When we talk about differentiable and continuous functions, if a function is differentiable, it means that we are capable of taking the derivative of that function at a specific point. If a function is differentiable, it means that it is continuous at that point, which means differentiability implies continuity. However, it is possible for a function to be continuous at a point and not differentiable at a point. So continuity does not imply differentiability. So what we're looking for in a continuous function is a sharp turn or a vertical tangent line. If you see either one of those two things, then the function is not differentiable at those points. So for the first example, we're going to describe the x values at which f is differentiable. So our first function is f of x equals the absolute value of x squared minus 9. In order to figure this out, the first thing we're going to do is we're going to go ahead and sketch a graph of this function. If the absolute value bars were not there, it would be a parabola. Because it's the absolute value of the parabola, the part of the parabola that's below the x-axis is reflected so it's above the x-axis. So essentially, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. The y-intercept is at positive 9. The x-intercepts are at 3 and negative 3. So the parabola would come down. Instead of going through, it bounces sharply and then bounces sharply again. So these 2 points on the x-axis are sharp turns. Because they are sharp turns, the function is not differentiable at those 2 x values. So describe the x values at which it is differentiable. We would have negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. For the next function, we have a rational function. So this rational function, if we factor the denominator, it would give us x plus 2 times x minus 2. So we know that we have vertical asymptotes at 2 and negative 2. Because they are vertical asymptotes, the function is not continuous at those 2 x values, which means the function is not differentiable at those 2 x values. So just by sketching the asymptotes, and we would have a horizontal asymptote at 1. So the function is going to be continuous on this side of the vertical asymptote, and then between the vertical asymptotes, and then again over here. So if it's continuous in those sections, it's differentiable in those sections. So the x values at which it is differentiable is from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity, because it's differentiable everywhere except those x values where the vertical asymptotes are, which disrupts the continuity, which also disrupts the differentiability. Our next function is a square root function. We'll have an x-intercept at 1, and then it looks something like this. Because the function does not exist before 1, we know that it's not differentiable there, but the point that's in question right now is, should 1 be included? So should we have a bracket at 1, or should that be a parenthesis? So as we sketch the tangent lines and we come around the corner and we're going to hit the tangent right at 1, that would be a vertical tangent line. Because that's a vertical tangent line, 1 is not included. So our differentiable region would be from 1 to infinity. So looking at your homework, my goal is for you to be able to look at functions and tell by looking at the graph or sketching the graph first, then looking at it, where these are differentiable. So I don't expect you to be able to do all of the complicated math behind why or why not they're differentiable at these points. I just want you to be able to pick out the points where it's not differentiable from a graph.